And assume, oh, I forgot about that. Anyway, assume that U is a subsolution, a viscosity subsolution. I'm going to Q viscosity now. It's boring to repeat it thousands of times. I have U x0 is the initial condition is equal to U0x equal to U tilde x0 for all x. So initial condition is the same. I forgot this, so that's why I add this. And assume that U tilde is a supersolution. Then we have U is always less than equal to U tilde. So this is the so-called comparison principle. Because once we have this, we have uniqueness because you take two solutions. U1 and U2, U1 is less than equal to U2, U2 is less than equal to U1. You apply comparison principle twice. So this is a so-called famous comparison principle. Okay, the big deal, the hard thing is that U and U tilde are not in C1. They are not differentiable. So how do you deal with them? How do you test them? How do you handle stuff? Because you see the definition of test function, everything has to be, the test function has to be smooth as such. So that was, just remain an open question. Actually, Hamilton-Jacobi equation is known for a long time. So Hamilton, right? But that's from classical mechanics. I'm going to go to classical mechanics a little bit later on. But this is only known in 1980s. This is a celebrated history of Hamilton and Jones. And one of the big deals that he did with this very influential career. So, how do we handle that? How do we manage to bypass the difficulty of not differentiable? So, actually, there's a device that was done earlier in the 70s by a Russian guy called Khrushchev. So, Khrushchev actually found a very, very clever method called doubling variable method. So Khrushchev, I don't remember, it's maybe 60 or 70s, or he found a very clever idea which is called doubling variable method. That by using this doubling variable method, he gets uniqueness of entropy solution for scalar transformation problem. This is a very clever idea. So he gets uniqueness of entropy solution for scalar transformation problem. So again, scalar conservation also it has many solutions. But entropy solution is kind of a selection procedure to give you the correct solution. It's like viscosity solution. So how does it go? And then Crandall and Leo realized that they can use the idea of Khrushchev doubling variable to handle the question of non-differentiability. And then by that doubling variable method, it now becomes a standard method. It's one of the main methods, viscosity solution, that actually we can overcome. Okay, so sketch a proof. Okay, along the way there are many terms. This is a method that once you do it by yourself, you get, when I was a grad student for the first year, I was too lazy to do it, and they say this is kind of too fancy, it's too hard. But when you see that you do it once, okay, just like that. Okay, I need to come. Okay, I forgot it. I need to put some assumptions on the Hamiltonian. So So some conditions on age. Of course, we have to put some condition on age on the Hamiltonian, otherwise it doesn't work very well. I have age p1 minus age of xp2. I mean those are quite general. We can modify those later. I just put some very ancient conditions. So this is just in P. It's not necessary, but just put it for simplicity. And then it's also Lipschitz in space, so Lipschitz in P variable and Lipschitz in X variable. By the way, this condition and this proof I follow Evans book, Evans PD book. Of course, I mean there are many proofs of this. If you want to see this, you also can go back to the paper of Crandall, Evans, and Young's in transaction of AMS in the 1980s. And then since then, there are many developments. I'm going to mention that. Okay, this is a sketch of the proof. Okay, the idea is the following. Instead of looking at u and u theta in one variable, you're going to doubling the variable. So xt is one set of variable, and ys is one more set of variable. That's double it. You double it. Because picture of the guy is not very nice, it's not differentiable. Actually, you see, in the assumption, I always assume that they're continuous. They're only continuous. You barely have anything about differentiability. So, we're going to look at uxt. Now, I'm going to avoid to put u theta xt. I'm going to double the variable. So, I'm going to look at u theta. U theta of ys, you see, I double the variable. You see. U now depends on xt and u theta depends on ys. Completely different set of variables. Now, because of doing so, I need to do some analyzation. Minus x minus y squared plus 3 minus s squared over epsilon squared. But I always split each of the term. It's a mess, but you know. So we double the variable. Okay? Now, when we double the variable, of course, we don't want x and y and t and s to stay too far from each other. So we put a penalization. X minus y squared plus t minus s squared over epsilon squared. So when we let epsilon goes to 0, this one going to go to infinity. Those were different. So they have to pull close to each other. Be close and close to each other. So this is a penalization to have x minus y and t minus s more. So, you know, you're going to see more in the proof. There are many ways to explain this doubling variable procedure, but in some sense, this and this are not differentiable. We're going to do the test function. We're going to kick the difficulty to the analyzation and test it and so on and so forth. So now, how about these two guys? Oh, we're going to consider the maximum of this, you know. Because we assume u and u theta are bounded, so we analyze it a little bit with this so that the maximum not t and s not going to go to infinity. And also, we don't want x and y to go to infinity. So this is to keep t and s bounded. This is to keep x and y bounded. Okay, you know, that's why I say it's such a mess the first time you see it, but it's like, you know, you are the one who designed the box. It's natural for you, but it's not natural if you are the one who just use the box. Like Google Map, you go to use Google Map. It's complicated. You just follow the what you don't know how to design. But if you were the one who designed, you would really do the same. Okay. So that's the idea. 15 minutes. good. Now assume a contradiction. That I have u is not less than equal to u tilde. I want to prove u is less than equal to u tilde. So assume a contradiction that it is not, then we do have that the supremum of u tilde minus u is equal to some sigma greater than 0, right? Rn equals 0. Right, so this has to be greater than this at some point. Okay? So now I'm gonna look at the phi of x dt. Okay, I'm gonna let ys equal to x3 to see what it is. It's gonna be u xt minus u tilde xt. When x and y equal to x and y and t and s is the same, this finalization goes to 1. And I have minus lambda t plus lambda 2t minus epsilon 2y squared. Right? So for example, we have that I think I put this up. U minus U